Hello! In this video, we'll analyze the performance of the pipeline processor. So consider the SPECint 2000 benchmark again with this mixture of instruction types, and suppose that 40% of the loads were used by the next instruction and caused a stall, and that 50% of the branches were mispredicted and caused two instructions to be flushed. Let's figure out the average cycles per instruction. Ideally in a pipeline processor it should be 1, but in reality there's some stalls that increase the CPI. So for a load, for the load word, it's 1 cycle 60% of the time, and 2 cycles 40% of the time is 1.4. Cycles per instruction for the branch is 1 cycle 50% of the time, and 3 cycles, the other half of the time when we mispredict, is 2. And so the average CPI is 0.25% for loads times 1.4 plus 0.13 for the branches times 2 plus the remaining 0.62 being 1 cycle, and that comes out to 1.23 cycles per instruction on average. Now let's take a look at the critical path. So we have to look at each stage to identify the critical path. In the fetch stage, we have a propagation delay through the PC register, plus a memory delay to read the memory, plus a setup time at the fetch stage register. For decode, we need to read the register file and set up the next register, and we need to do that in half the cycle, so the entire cycle time has to be at least twice that. For execute, we need to come out of the first register through, there's a total of 4 muxes if we look carefully in the decode stage. There's the ALU, then there's time for the AND/OR gate to do the branch logic, and then we have to set up at the flip-flop to update the program counter. In the memory, we have a propagation delay out of register, time to load from the data memory, and set up at the next register. And for write back, in half a cycle we need to come out of the first flip-flop, go through a mux, and write the register file. And that has to happen in half a cycle, so the cycle time needs to be at least twice that. So we could put in the numbers for each of these and see what the maximum clock period needs to be. And we find that the slowest case is in the execute stage. So here we have, let's say we need to forward a value to a branch instruction. So the source is coming from the pipeline register here, either one of these. It goes into a mux, the result mux. We get that result value. Now let's say we needed to forward it, so it has to come up through one of the forwarding muxes. Then it can go into the ALU source B mux, and now we finally have source B. So the ALU can then use that source in a comparison for a branch and get the 0 flag. That 0 flag goes through the AND/OR gate and then to the next PC mux. We choose the source, and finally the program counter is ready for the PC flip-flop. So that's our longest path, and we find TPCQ is 40 picoseconds plus 4 muxes, each with 30 picoseconds, plus the ALU is 120 picoseconds, plus the AND/OR logic is 20, plus a setup time of 50 is giving us 40, 120 makes 160, 280, 300, 350. So 350 picoseconds. It's not quite as good as the 200 picoseconds we hoped that we might get with just the memory read being on the critical path, but it's still a whole lot better than the 750 of the single cycle processor. So now if I have a program with 100 billion instructions, just 100 billion instructions times an average of 1.23 cycles per instruction times 350 picoseconds cycle time gives us 43 picoseconds to execute the program. So in comparison, our single cycle processor took 75 picoseconds. Our multi-cycle went up to 155 picoseconds, which is about half as fast as the single cycle. So that was not a speed up, although it did save hardware. The pipeline processor costs some extra hardware. It costs more pipeline registers, but it can execute our program in only 43 picoseconds, which is 1.7 times as fast as the single cycle processor. So getting a 70% speed up is a huge deal on a processor, and getting it just for the cost of some extra registers is a very good trade-off, and that's why nearly all processors today are pipelined.